In this video, we're going to talk about even and odd functions, and we're going to also talk about trig function transformations. Even and odd functions is a math topic that we don't see a lot on the ACT, but every once in a while it does show up. So we're going to give you an overview of even and odd functions so that you would be able to answer any questions that you may find that come up with even and odd functions. By definition, a function is even if when you plug in negative x, so if you have f of negative x, it's the same as f of x. So anytime you plug in that negative x, you're going to get the same result as when you plugged in x. Most applications that we see of this appear graphically. So when we want to look for a function to be even, it's when it is symmetric about the y-axis. And this is an example of an even function. If you would look at this parabola, you would see that it is symmetric about the y-axis. We could almost fold the parabola over from left to right, and it would be symmetric about the y-axis. That makes the function even. Now for odd functions, by definition, f of negative x, plugging in this negative x equals a negative f of x. So the result is negative of whatever you've plugged into for x. Again, graphically, what we're going to be looking for of this is that if a function is odd, it's symmetric about the origin. And we have this example here of this graph. It is symmetric about the origin. And a lot of times what I like to use to determine symmetry about the origin is using the 180 test. And what that is just imagine rotating your graph 180 degrees. After the 180 degree rotation, if the graph looks the same, then it's symmetric about the origin. And in this case, we can define it as an odd function. So I think of odd function, the O in odd, think of O for origin, symmetric about the origin for odd. If it's even, it's symmetric about the y-axis. So functions can be even, they can be odd, or they can be neither if they're neither even or odd. So if you try either one of these algebraic, plugging in the negative x and evaluating it with f of x, or if you look at the graph and either of these fail, then you would say the function's neither even nor odd. And this is an example of that. We have this line, f of x equals x plus 3. It is not symmetric about the y-axis. We could not fold it over the y-axis. It would be different. And it is also not symmetric about the origin. So this function is neither even nor odd. Now let's take a look at some of our trig functions and graphing those. When we're talking about sine and cosine, we can look at the graphs of these functions, and it's a good idea to be familiar with these. So first of all, let's take a look at f of x equals sine x. This is a wave function. If you can remember specific points here, the sine function is going to pass through the point 0, 0, and it will go up to the y value of 1 at pi over 2. And then it crosses the x-axis again at pi. And it is a function, a repeating function. It crosses the point 0, 1, if you'll notice how the graph, again, it's a repeating function, a wave function that has minimum points and maximum points. Our maximum point that we see here occurs at 0, 1, and that's where it will cross the y-axis at that point. So you can see how these differ. Think about the points that are included on a sine graph and which are included on the cosine graph, and you can also make use of your unit circle to find these points. So be familiar with how these look. Let's do a little review. We just talked about even and odd functions. When we look at our sine function on the left-hand side, is that function even or odd? Remember what we said about symmetry. Sine function is going to be odd because it is symmetric about the origin. We can do the 180 test. Now looking at cosine, is that even or odd? Looking at symmetry, we can tell that cosine graph is even because it is symmetric about the y-axis. We can almost fold that graph in half and see that we would have the same thing on the right side as the left-hand side. So that's symmetric about the y-axis. Now let's take a look at our sine and cosine functions and how we might have some transformations that occur with that. This is the general form of the sine function where we have this a, b, c, and d in our function. Same thing for cosine. Same form except for one function has sine in it, the other has cosine in it. Let's see what each of these variables a, b, c, and d represent. So when we're talking about a, the absolute value of a, that is our amplitude. It's going to be a positive value when you give the amplitude. We're going to take a look at each of these in the following slides, but for right now we'll just give the definition. 2 pi over b, that b that's in our function, represents the period. C over b is going to be a horizontal shift. And this is important here because when you notice the general form of both of these functions, we have a negative sign in the formula, a subtraction. If C over B turns out to be positive, we're just looking at C over B, we're going to move it to the right C over B units. If C over B is negative, we'll move to the left C over B units. If you're just looking at the function, some people look at that, and if we keep the minus sign in the graph itself, we're going to be a move to the right, opposite the sign, sometimes people say. If it's a plus, it would be a move to the left. And we'll look at an example and you'll see this. D represents the vertical shift, up if positive, down if negative. And so that takes the sign of what we're given in front of the D. This is very similar to when you ever have a transformation of just any other graph. When we look at a line, y equals x, that's the graph of a line. Y equals x plus 3 means we shift the graph up 3. And we actually looked at that in the previous slide when we were determining even or odd. We just shift the point from 0, 0, where y equals x crosses, to the point 0, 3 when we have y equals x plus 3. Same thing we're doing here, just sine and cosine functions. So you may see some questions related to each of these terms, a, b, c, or d, and how that will affect the transformation of these functions. Now let's take a look a little bit closer so maybe you can visualize and see what we're talking about here. The function f of x equals sine x, remember, is a repeating pattern of a function. In the little glimpse that we're looking at here, we'll cross the x-axis at negative pi, 0, and pi. That's what the y, or f of x equals sine x looks like. Now we talked about amplitude a, the absolute value of a. That is half the distance from the highest point of the curve to the bottom point of the curve. So our maximum to our minimum, and we're going to take half of that. So our purple arrows show what the amplitude would be. With our normal f of x equals sine x, where we have our midline at the point 0, 0, we're going to go up to 1 for our maximum and down to negative 1 for our minimum. So in this case for sine x, our amplitude is a 1. That's the value, the understood 1 in front of the sine x. That's our amplitude. Now for period, which is 2 pi over b, we talked about that in the previous slide, we're talking about the distance between each repeating wave of the function. So from one tip of the function's graph to the next tip. And the example that we chose here, our pink line, shows we're looking across y equals negative 1, and that gives us, in this case, a distance of 2 pi. And that's what it is. For f of x equals sine x, the natural period is 2 pi. You may be able to see it here a little bit better. Because with period, we're just looking for that repeating point. You can pick any point. The first point I chose was the minimum, from minimum point to minimum point. The darker pink line here I'm showing you, it's where it's crossing the x-axis after we're coming from the max down to the min, goes from negative pi to positive pi, and that's a distance of 2 pi. That is one period of the sine graph. And we're showing all these examples with the sine graph, but you can do the exact same thing with a cosine graph. You just use the cosine graph function. Now let's take a look at some shifts with the sine function. In the reddish color, we have regular f of x equals sine x. In the blue g of x, we're going to show sine of x minus pi over 2. The minus pi over 2 is in the parentheses. It's part of the sine, the angle of the sine. So notice how with this, we're going to have a horizontal shift. That means left or right. A horizontal shift right pi over 2 units. We have in our original function x minus pi over 2. So this is where I was talking about a lot of times people say it shows the minus. It's going to be opposite what we think of minus. We usually think minus going to the left, but it actually goes to the right in this case, but we can prove that. But this is really what you need to, if you can just remember that minus sign is going to mean right pi over 2. So we shifted, instead of crossing at, let's say, 0, 0 in the red graph, now we're crossing at pi over 2 for the blue graph. Everything shifts to the right pi over 2. That's a horizontal shift. Now we'll take a look at a vertical shift. So here we have, again, our original function in the red color. G of x is our shift. That's sine of x plus 2. This time the plus 2 is outside of the parentheses. It's not a part of the sign. And that indicates, that was our D, indicates a vertical shift up 2 units. So instead of crossing now at 0, 0, we will cross at the point 0, 2. We shifted up 2 units. Every point of the sine function shifts up 2 units. This gives you that graphical view. Now let's take a look at an ACT type example where we can apply these things. Pause the video here, try it out for yourself, and we'll come back and work it together. The question says, what is the equation of the sine x graph with a period of 2 pi, an amplitude of 3, and a downward shift of 2 units? So these are all parts of that transformation function that we've looked at. So our general sine function, we're talking about a sine graph, is given in this form that we have. We were told that we had an amplitude of 3. To me, the amplitude's a little bit easier. It's the easiest thing to look at. The amplitude goes out in front of the sine function, so we know that's 3. If we glance at our answer choices, we see all of them have a 3 as an amplitude, so we can't eliminate anything yet. But next we can look at the period. By definition, period is 2 pi over b. So we can solve for b in our case because we're given that the period is 2 pi. So if we do 2 pi over 2 pi, that gives us 1. b is equal to 1 in this case. So if we can plug that in, we know that the term in front of the x is a 1. We could go ahead and eliminate a and b because they have a 2 in front of those. One more thing that we're given is that we have a vertical shift down 2 units. So that's going to make D a negative 2. We're going down 2 units. F of x equals to negative 3 sine x minus 2. And that's answer choice D.